Nim Games. Nim can be played with objects such as beans, stones, or matchsticks. Lay out several piles with each pile containing an arbitrary number of objects. The two players take turns to remove any number of objects from a single pile. It's also possible to take the entire pile. Thus, the total number of objects decreases at every taking. The player who removes the last object wins the game. On the picture, the player removed 5 matchsticks from the top row. Note that the order of the rows doesn't matter, and thus it is better to think about them as piles. The first recorded discussion of Nim dates back to 1902, when the mathematician Charles Leonard Bouton published an article on its solution. He also coined the name Nim, taking it from the German verb nehmen, imperative form Nimm, meaning to take. Obscurity clouds the origins of Nim, as many nations claim to have invented it. It closely resembles the ancient Chinese game of picking stones. In Europe, Nim became popular following the 1961 Alain Resnier film, Last Year at Marienbad. Below is a clip from the film. Nim games can be played on the chessboard too. The objects are counters, and piles are rows of counters. Players take an arbitrary number of counters from the row of their choice. The player who takes the last counter is the winner. In the position below, the winning strategy is to create 2 rows with equal number of counters. This can be achieved by removing the entire bottom row. Hence, we get to the second position, in which we simply copy the opponent's move. For example, if he or she takes 2 counters from the top row, then we remove 2 from the bottom row, and so on. This way, we will take the last counter and win the game. In a Nim game with a single pile, the first player wins by removing every object in the pile, or every counter in a row if the Nim game is played on the chessboard. In any position with 2 rows of equal length, the second player can win. The copycat method is well known in game theory. The simple idea of copying the opponent's move often yields positive results and therefore is a part of many winning strategies. It even has a special name, Tweedledum, Tweedledee, after the twin characters of Lewis Carroll's book Through the Looking Glass. If there are 2 rows of unequal length, then the player whose turn it is must remove enough counters from the longer row to make the 2 rows equal in length. Let's continue our investigation with more complex positions. There is a foolproof method that, if followed consistently, will ensure success from a winning position of any Nim game. We shall discuss this here without looking deeply into the mathematical proofs that underpin it. Here is a game of Nim made of 3 piles of matchsticks. The first step is to arrange the matches in each pile into groups of 4, 2, and 1. We now have one group of 4, 3 groups of 2, and one group of 1 matchstick. The second step is to remove some matchsticks that leave an even number of each group on the table. As we can't create 2 groups of 4, we must have none instead of 1. The groups of 2 and 1 must also become even, which can be done by removing 5 matchsticks from the top pile, leaving us with this position. This is the familiar Nim position with piles 1, 2 and 3. No matter what our opponent does in the next move, we can create 2 groups of equal size, either 2 2s or 2 1s. After that, we simply copy the opponent's move, or, in the language of game theory, we use Tweedledum, Tweedledee to win the game. Let's repeat this Nim game on the chessboard with counters. The first step is to arrange the counters in each row into groups of 4, 2, and 1. We do this by color coding the groups. If we find 4 counters in a row, then they will be colored green. Remaining groups of 2 counters will be colored blue, and the leftover single ones in red. The winning strategy is to leave an even number of each colored group. We cannot leave 2 green groups, so the green counters need to go. Now, 3 blue and 1 red group would remain, and we must turn that into 2 blue and 2 red groups. There is only one way to do this, by removing 1 blue counter from the bottom row. The last step is to get the coloring right in the resulting position. We need to recolor the remaining single counter from blue to red before we let our opponent make his or her next move. In this position, there are an even number of each colored groups, namely 2 groups of green, 2 groups of blue, and 2 groups of red counters. Charles Leonard Bouton called this a safe combination. Just to remind you, Bouton was the mathematician who published an article on the solution of Nim in 1902. Bouton also proved the following 2 statements. If player E leaves a safe combination on the table, player B cannot leave a safe combination at his next move. It is always possible to move to a safe combination from an unsafe combination. On the bottom left diagram, there is an unsafe combination with an odd number of each colored group. We can turn this into a safe combination by removing 5 counters in the second row. The bottom right diagram depicts a safe combination indeed, with an even number of each colored group, 2 blue and 4 red groups. A safe combination is a lost position to start from. See the bottom left diagram. No matter what move player A makes here, it will result in an unsafe combination. For example, if he or she removes 5 counters from the bottom row, the resulting position shown in the middle diagram will be an unsafe combination. Player B can turn this into a safe combination by removing 5 counters from the second row. Take a look at the bottom right board. There are 2 blue and 4 red groups, so this is indeed a safe combination. Let's follow this Nim game to one of its possible conclusions. With correct play, safe and unsafe combinations alternate. Player A is always presented with a safe combination, which he or she reluctantly turns into an unsafe combination. Player B can win the game by creating safe combinations with ever-decreasing number of counters until there are no counters left. The position with 0 counters will be the final safe position on the board. You may ask, why should we play Nim on the chessboard when it's simpler to do it with matchsticks or piles of stones? The answer is that we do like to play several strategy games on the chessboard, which are Nim games in disguise. One of these games is Sliding Rooks. Let's recap its rules. Place 8 white rooks on the left side of the board and 8 black rooks on the right-hand side of the board. The rooks can only slide sideways, not up and down. The white rooks can only move rightwards, and the black rooks can only move leftwards. Capturing or jumping over pieces is not permitted. The last person to move is the winner. Let's place counters between the opposing army of rooks. With each move, a number of counters are removed from a single row until no further moves are possible, which happens when all counters are gone. So Sliding Rooks is essentially a Nim game, and any winning strategies that apply to Nim will also apply to Sliding Rooks. If we color code the counters, we get 8 green and 8 blue groups, which is a safe combination. We know from our Nim studies that a safe combination is a losing position for the first player. Hence the second player, namely black, has a winning strategy in Sliding Rooks. Black can create safe combinations with a simple tweedledum tweedledee in every move. As rows are interchangeable in Nim, it doesn't matter in which row, or rank as it's called in chess, the black rook copies white's last move. For example, in the first position, white moved the rook in the 7th rank, and black mirrored this move in the 8th rank. Any other rank, apart from the 7th rank, would have been equally good. Similar argument holds for the second pair of moves. White's second move was rook to d4, which was mirrored by rook to e2. Apart from the 4th, 7th and 8th rank, black can choose any other rank for the copycat move. Instead of tweedledum tweedledee, it is of course also possible to think about creating safe combinations by leaving an even number of each colored groups. A variant of Sliding Rooks is played with 7 pairs of rooks. Same rules apply as in the original game. Who has a winning strategy here? Well, there are 7 groups of green and 7 groups of blue counters, which is an unsafe combination. The first player, white, must create a safe combination to win. It can be done by moving one of the rooks to the G file. It is indeed a safe combination with 6 green and 6 blue groups. As a final exercise, let's look at the game in progress. White moves in this position. Who can win this game? Let's turn these sliding rooks into a Nim game. Having color-coded the counters, we find 1 green, 3 blue, and 3 red groups, which is an unsafe combination. Hence, white can win by creating a safe combination. There is only one way to do this. Can you find it? I give you a little time to think about the one and only winning move here. The only way to win is by moving the rook to e8. Now there are an even number of each colored groups, 4 blue and 2 red, so this is a safe combination. Well done if you have found it.